Okay, so the last speaker today this afternoon is by Professor Lei from Georgia Institute of Technology. He's going to talk about Habiro ring and unified quantum invariance of stream network.
Thank you. First, I would like to thank the organizers for inviting me here. It's a beautiful place. My talk is about the Witten-Reshetikhin derived invariant of three manifolds, but I have to begin with invariant of knot and links in S3 first. So let me recall that Jones polynomial discovered by Jones in around 1984 is an interesting invariant. So this is an invariance of frame. So I will use the frame version, oriented links in S3 to the ring of Laurent polynomial. So I will use the variable cube to 1/4, which satisfies the following skin relation. So because it's the skin of the frame version. So this relation means that if you have three links in S3 which are identical everywhere except for a small one in which this is the first one, this is the second one, this is the third one, then the invariant will satisfy this equality here. The second one is if you have an unknot which is far away from a link, then the value of this should be, value of the unknot should be quantum 2 times just the value of L, where I use here quantum n will be q to the n half minus q minus n half over q 1/2 minus q minus n half. And the last is the framing correction factor. So this is if you increase the one component of the link, increase the framing by 1, the factor will be 3/4 this one. So this is the famous Jones polynomial. Jones discovered this using when he discovered a special representation of the break group using subfactor. So use it, but the main thing is that he has this is a, so one Jones here is a representation of the break group using subfactor, and then use the Markov theorem which relates a breadth to length. And the main thing is the representation of break groups here is an object called the R matrix. Soon after that, there are many generalizations, mainly focus on, just if you have a good R matrix, you can build representation of break group, and then you can use Markov theorem to produce links, not links invariant. And there's the school of Matveyev in Leningrad, and Rina was part of that school. And then Jimbo and Greenfeld, they found a lot of R matrices. And then Reshetikhin and Dure formalized all this machinery into a big theory. Then it turns out that to every Lie algebra, simple Lie algebra, and every representation, you can build an R matrix, and then from there you can construct knot and link invariant. Okay. So at the end of the day, you have the following. Suppose G is a simple Lie algebra. And L here is an K component framed orientably and then you are given KG models. So V1 up to Vk here is our finite dimensional G model. Well, in the formal theory, you need the model of the quantized enveloping algebra of G, but the Grothendieck ring of that algebra is isomorphic to Grothendieck ring of the classical just the Lie algebra. So you can just speak about you can just assume that they are finite dimensional G models. Then you can define an invariant which is a Laurent polynomial. So G, I do know this J sub L, V1 up to Vk, comma Q, which is a Laurent polynomial in a fractional power of this quantum perimeter Q, where, well, this number D here, you can take it to be, say, two determinants of the Kaplan matrix of G. Okay. It's just some integer. So usually we say that, well, this is the Kerner Jones polynomial. Okay, the components are colored by G models. Okay. So in the simplest case, when G is SL2, well, SL2C. So here, this is just the set of all 2x2 traceless matrices, and you have the fundamental representation, which is a two-dimensional. Well, 2x2 matrix just acts naturally on C2. So V C2 here is the fundamental representation, and then you can define Vn, which is the symmetric power of order n here of T. This one is the unique, irreducible, and dimensional SL2 model. Okay, so I just write n for V sub n, and so I will have this JL of n1 to nk q. So each n here stands for the corresponding n-dimensional representation of SL2, and in this case it's in Z of q plus minus 1/4. So in this case, the Kaplan matrix has determinant 2. Okay. I'm not going to define this one here, but I'll give you a recipe to calculate this. Okay. So this is the so this is the if one component if a color is 1. So if color is 1, you can replace this by 1. So this means you just remove that component and that's it. Okay. If all the colors are 2, so I do right here. So JL of 2, this is simply the Jones polynomial that is determined by the skin relation here. Okay. I mean, if you have the skin relation, it's very easy to calculate. I mean, it's easy to show that there exists a unique invariant, well, at most 1, satisfy this condition. Okay, it's a bit more difficult, but not very difficult to prove the existence. And actually, one of the best proof is to use the Kaufman bracket. Okay, so if all the colors are 2, then it's just this version here, the frame version of the Jones polynomial. Okay, and if one of the colors is 1, you just remove that component. And then we have the following recurrence relation. If the color is n here, you can replace this by, so first you double this component using the framing, because it is framed, so you just take the parallel of that. You color one of them n minus 1, and the other is 2, then minus this one. Okay. So for example, sorry, n minus 2. So for example, if you take, so this is the figure 8, right? And I color this by 3. So this should be, I just draw this again. But I have to double this. Okay, so I color this 3. So this means that it's also 2 and 2, and then minus just this one again, color by 1. But color by 1 means that's just 1. So and 2 with 2 here is just the usual Jones polynomial. Okay. Okay. So so let me give an example here. I will property, just write only the tripoints and two formulas of the color zones of the tripoint. So the right hand tripoint is this node here. So it's JK of n, and I will divide by n quantum, which is actually the value of the unknown, also color white. So that will be 1 minus some from 0 to infinity q minus kn, 1 minus q 1 minus n, and then 1 minus q 2 minus n, 1 minus q k minus n here. So if you use the usual notation, so that's 1 minus n and q sub k. Okay. Now, so already, just like Don already mentioned today, I can replace this by just n minus 1, because whenever k is bigger than or equal to n, this is 0 here. Okay. But again, I would prefer to leave infinity here, and I will for a very good reason. So another formula. So this was obtained in my journal book with a student of mine, Win, and another formula due to Habiro is the following. You can write here sum from 0 to infinity. Okay, q minus k plus 3 over 2, and I also write q minus kn product from 1 to k, and this is what 1 minus q n plus k. So the first one here, this one is for n bigger than or equal to 1, and this one is for n just not 0. Okay. If n is not 0, any integer, this sum will be sum terminates and you have a finite term. Okay. But actually, to a little bit forward, I would say that so when n is equal to 0, both will be infinite sum. Okay, and they are actually the same. Well, if n is less than 0, the first is an infinite sum, the second one is a finite sum, but actually they still are the same. And actually they are the same in the so-called Habiro ring, which is the subject of also main subject of this talk. Okay. So the same in the Habiro ring. And this is well, in any case, they are both the same in Habiro. Okay, but if n is bigger than 0, both are finite sum. If n is less than 0, this is an infinite sum, and this is still a finite sum. Okay, and in general, it's pretty difficult to find compact formula for the color zones like this one here. There are a few due to Habiro, due to myself, and Saki Suzuki here also has some formula for the build-up of some nodes. Okay, so this is the color Jones polynomial, and then well, so the Jones polynomial is defined through either Reidemeister. I mean, we can define links as the class of link diagram modulo Reidemeister move. Okay, or you can use closure of breadth and Markov theorem. So it doesn't offer much, I mean, relation. We want to understand the Jones polynomial in terms of classical topology. I mean, we want to find an intrinsic definition of the Jones polynomial using the classical invariants like the fundamental group. Or you want to generalize the definition of the Jones polynomial to knot and links in three manifolds. Okay. So Witten came up with a definition which he claimed is an intrinsic three-dimensional definition of the Jones polynomial. Well, in terms of a Feynman integral, which we don't know how to make rigorous. However, what he said is that you can generalize the Jones polynomial to invariant of a pair which is a link, a frame link in a tree manifold. So we have L, M, where this is tree manifold, closed-oriented tree manifold, and L is a link in there, and then he claims that you can define invariant of this pair. Okay, but however, only at root of unity, instead of this Q here must be a root of unity. And then Reshetkin and Tue came up with the rigorous realization of this type of invariant. So now we call this the Reshetkin Tue invariant. And I will only define, well, actually give the definition of the WRT invariant, which will go by tau, which depends on a tree manifold M. So I will drop the link. Well, I will define, well, it can be defined for any simple Lie algebra, and then a root of unity with some restrictions. So this is the invariant. So G here is still a semi-simple, I will just a simple Lie algebra. N here is oriented, closed, tree manifold. And psi here is a root of unity of order, so I will just some order, I will also fix the number R with some restriction. I'm not going to specify these restrictions here. So I will give the set Z here is the set of all roots of unity, and then Z sub G is the set of all roots of unity subject to these restrictions. Well, maybe I spell out this here. It's at least the set of all, this number R should be bigger than or equal to the so-called dual constant number, and then R must be divisible by the square of the length of the long root over the length of the short root. Okay, so usually this is either square root, either 1 square root 2 square root 3. So square this square number will be 1, 2, or 2. So it means 1, 2, or 3. Okay, 1 is simply lays 2 for the BCD series. Sorry, for the A, C, D. Okay, I'm not going to into the detail of this here. Okay, so let me at least give the definition of this invariant for SL2 case. Okay, so now suppose G here is SL2, and M here is the result of, so I write here S3 sub K, so it means that the result of surgery on a knot K, along the knot K in S3. Okay, well, K here is the frame knot in S3, and the framing, I think is some number F bigger than 0. Okay, so some special cases to give you just for you to be to see how the invariant is defined. So psi here is any root of unity. So in this here with the order bigger than or equal to 2. So this is going to this one here. Okay. So we define f k of psi. So order is equal to this number r here. So we define this as a sum. So first I take j k n, and I times n, which is the value of the unknown, and there's reason for this. Why we have to multiply by this quantum n, which comes from TQFT. Okay, so we do this, and then we evaluate when Q is equal to this side. Okay. And as Don already mentioned today, there's some symmetry here, some periodicity. I mean, once you fix something at root of unity, then everything will be periodic. Well, actually, the period is 2n, so I will end from 1 to 2r. Okay. I mean, because this is the yes.
So how it is normalized on the unknown? Is it still what?
So first I define fk of psi here.
No, GK. You should normalize the quantum n.
Well, if if we use the definition I explained here, then for the unknown is continent. Okay, that is the only functorial normalization. Otherwise, it's not functorial. Okay, so yeah, so this I define fk of R here. So as I said, I mean this is when Q is an order of unity, and you look at this as a function on the color n. It has period dual. Okay, and so we want to take the sum over all colors. There's a simple, pretty simple argument to show that this sum will be invariant under the hand-on slide move, I mean Kirby move. Okay. The only thing is that infinite sum, when you take the sum over all colors, is not well defined. And there are several ways to regularize such a sum. One of the ways is to focus at root of unity. Then, because of the periodicity, you just take the sum over a fundamental of that periodicity. Or if you want to use general Q, you take integral and then you use some kind of regularization of the integral. Okay, so this is the one way to regularize this infinite sum. And then tau m of SL2 at whose sign here is equal to, I take fk of psi, and I divide by f u plus of psi to the f. So remember, f here is the framing. Okay, and the u plus here is the not with positive, the unknown with framing one. Okay, so that is the definition of the WRT invariant of SL2 when the three manifolds is the result of filtering on a knot with framing f, which is bigger than 0. There are many questions about this. Well, certainly the most interesting question is about the topological interpretation of this. But I'm not going to discuss that today. We want to understand, so when this was defined around 89 or 90, so at that time I was at the Max Planck Institute, and Maxim Kontsevich told me that these numbers here should be algebraic integers. Okay? And a bit later, Ruth Laurent independently formulated that as a conjecture in one of her papers. So we have a question here is tau m g sinus. So algebraic integer. So there are some philosophical explanation for this. So Kontsevich said that it should be something like some intersection number, something like that. So there are integers in some sense. Well, if you want to categorize these, you need some integrality also, something like that. Okay, and we want to understand relation between various. See, if you have a root sign here, you have another root, and so on. I mean, we want to understand this is a function. So I get tau and g here is the map from z to c, and want to understand what kind of function can you get here. Okay, and it turns out that we will get the type of function that we get is what we call here. I mean, this function is a function in the Habiro ring. It's a very interesting object. We term it, I mean, the class of analytic function on the set of roots of unity. And I'm going to now to explain what is the Habiro ring. And actually, the Kashev invariants are all in the Habiro ring. Okay, so this is the Habiro ring. So the definition is very simple. So ZQ hat here is just some completion of the ring of Laurent polynomial with integer coefficients. And I want to emphasize this integer coefficients here. We take the inverse limit ZQ, and we divide by this Q sub n. So let me recall that already this morning we saw this 1 minus Q up to 1 minus Q to the n. Okay, so 1 minus Q times 1 minus Q squared and so on. So you take this inverse limit here, and you get a ring. So let's first consider the first example. So call that q n plus 1 here is simply 1 minus q to the n plus 1 times the original one. Okay? So if I multiply this out, you see that q sub n plus 1 here is equal to q sub n minus q n plus 1 times q sub n. Okay? So let us move this to the left, move this to the right. See that q to the n plus 1, q sub n is equal to q sub n minus q sub n plus 1. And now we take the sum, and from 0 to infinity of this one here. And what will be on the right hand side? This telescoping series will cancel except for the very first term, and the first term is just 1. So you see that 1 is equal to the sum, and from 0 to infinity, q to the n plus 1, q sub n, which is an element of this one here. So informally, every element of this can be presented as an infinite sum. Sorry?
1 was already in the ring, it just as 1.
Right, yeah. So, but I
This just shows that the representation is not unique.
Right, yeah. So if f is in this Habiro ring, then there exists a presentation of the form f sum f and q, and then q sub n, where this f and q is in here. Okay, but I want to say that this presentation is not unique. You see that one can be presented in such a, in another form here. Okay, but for example, it's not very different, but it's not quite obvious. Q inverse is in here. Okay, but you see that if I just multiply by Q inverse here, I guess just Q inverse is equal to the sum Q to the n and then Q sub n coming from this. Okay, so Q inverse is in that ring. And actually this presentation is unique. I mean, so there's no uniqueness, but if you impose the condition that the degree of f of n less than or equal to n, then it's unique. It's unique. That's an easy exercise. Okay, so what are the properties of elements of this Habiro ring here? The first one, which I use by 0 here, is that if q take value psi, which is an element in this set of root of unity, then when you place qi just here, this sum terminates. Okay? So we can define what is f psi, which is just the sum, just the f and psi of psi sub n. And now you only need to take n from 0 to r minus 1, where recall that I only use r as the order of psi here. Okay? There's always a finite sum terminates. So every element in this Habiro ring gives a function with an f in zenith q. Then you can consider this as just a set or function from z to c here. Okay? Well, now the first interesting property is that this class of function here, each function is in class C infinity. But you can differentiate as many times as you want. Okay, so why? What happens if f is like this and you take the derivative? So f prime or d over dq, take, well, the thing is that what is q n prime? So that is 1 minus q squared up to 1 minus q to the n, right? Okay, and you can easily show that this is divisible by qq sub n minus 1 over 2. Well, integral part. Okay, you take derivatives, just remove one of this, you still have a run of at least n minus 1 over 2 either from the left or from the right, and that is divisible by this here. Okay, so it means that the derivative function is actually a function from zq hat to zq hat, continuous in the topology of this completion here. And so we can take derivative of a function and we can do derivative again, and so you can take derivative as many times as you want. So you can also define for every sign in the domain, you define the Taylor series. Okay. That will be the sum. You take the n derivative as usual, xi over n factorial, and then q minus sine to the n. And that would be, so in general, this would be a number in C, okay? But it's easy to prove that actually this is the in Z sine of q minus sine. Okay, so the coefficients are actually in this integer ring. And the main theorem about Habiro ring, so this is Habiro, I would say that most of what I said here is a joint work with Habiro. And this is just Habiro theory. So first of all, so remember that in theory of analytic function, if two analytic functions have the same Taylor expansion at just one point, then they are the same. Okay, so here we have exactly the same. It means that if so suppose we have f and g are in the Habiro ring. So the first is that if the Taylor expansion f is equal to the Taylor expansion of g for some psi in the domain, then f is equal to g. Okay? And then the second one is that if f of psi is equal to g of psi for every psi in a subset z prime of z having a limit point, but in some topology, in the so-called cyclotomic topology, then f is equal to g. Okay? Probably I skipped the description of the cyclotomic topology here. I just wanted to say that, or maybe I give quick definition of. So psi is the limit point of z prime if there exist infinitely many psi prime in z prime such that the order, so recall that each here is a root of unity, so you just consider the order as an element of the group is the prime power. The prime power. So, and then from here you can recover the topology. The essence of the topology is this. Okay? So for example, if I look at the set of all zeta, say 3 to the k is in n. Okay? So this one has a limit point which is 1. So 1 is the limit point of this. Okay, and 1 is also limit point, say I take zeta p, but p is prime. Okay, and again I use the notation that don't use today, so zeta capital N, or maybe use as R, is e 2 pi I over r here. So so the theorem would say, for example, that the whole function is determined by the value at this point. Okay? Okay. And I want to emphasize that this is the ground in Z is very important here. For example, if if we look at this here, we look at the Taylor expansion at 1. Well, another way to understand the Taylor expansion at 1 is that 1 minus q to the n certainly divides q sub n. Okay, because this is just product 1 minus q squared, and so on. So you have the map from the inverse limit of zq 1 minus q to the n, and you have to the inverse limit of zq and then q sub n. Okay, I mean this one give us this one here. Now the inverse limit of this is exactly z of Q minus 1. So that's map 2, and this is the Habiro ring. So, thank you. So this is the Habiro ring. And this is exactly the Taylor expansion at 1. So this is just T1 here. Okay. So put it in a simple way. You just write, I mean, if you have here the sum of f and q, and then 1 minus q, 1 minus q squared, up to 1 minus q to the n, what you do is just rewrite this everything here as in polynomial in q minus 1. Then this is a polynomial q minus 1 divisible by q minus 1 to the n because of this here. And so you can easily write this in a formal partition in 1 minus q, which is the Taylor series here. Okay? And the theorem to say that this is an injection, right? And this is determined by the Taylor series, means that the Taylor series map is just an injection. And so this means that.
Excuse me. Why is t psi of f in what you wrote? Why is this formula true at the top of the board? Top.
This one?
Yeah.
Why this one?
Yeah.
So I said that this is an easy exercise.
Yeah. Okay. Well, in that case.
Okay. So let me give you another. I mean, again, I mean this 1 minus q times 1 minus q squared times 1 minus q to the n here is divisible by a high power of q minus psi. If you fix the psi, this is equal by this, and then you just rewrite this in this form here, and that must be equal to this, which is this proof
it's enough to get the n factorial.
Right. Yeah. Okay. Okay. Where is that? Okay. So this is an injection map. So in particular, because this is a domain, this is a domain. So this must be a domain because this is injection. Okay. So this is a domain. I mean, this Habiro ring is always a domain. However, you can do the whole thing exactly the same thing, but now replace. If we can replace z, the bounding z in here by for example, I can replace by q or by the z of 1 over d here. So you also have this text, so that is the Taylor expansion here, z of q to z of q minus 1 here. Then this is injective, but not surjective. Okay, it's injective, but it's not surjective. Injectivity is the first part of the theorem. Not surjective is not very difficult to show. However, if I replace this one by q, then you can define the Taylor expansion exactly the same way, and you get here q minus 1. And now this map is quite opposite. Now it's surjective but not injective. And actually this is not a domain. And simply if you replace this by z 1 over d, where d is not 1, positive integer, there is not domain. Okay, so I have 5 minutes, right?
You 10 minutes.
Okay. So maybe now it's time to formulate the theorem. So the theorem that is proved in joint with Habiro is that for every simple Lie integral, for every 3 manifold, so I always mean oriented compact or closed, so 3 manifold n. Only 3 manifold, but integral homology 3 spheres. So it means that the homology of n with coefficient in z is the same as that of S3. There exists a unique invariant that I know by J sub n, also G here, in the Habiro ring, such that for every psi in Z sub G, where you can define the Witten ratio taking to right invariant, this agree with that. So J and is equal to tau and G of psi here. Okay, so and this is a so-called case when G is less than 2. It was the first proved by Habiro a few years ago when he also developed the theory of Habiro ring. Okay, but so far we cannot generalize Habiro's proof to general simple Lie algebra, and we have to use another proof, which in a sense more conceptual than the original proof. Maybe I also mention here that I prove sometimes, although I never wrote up the proof. So for every simple Lie algebra, the so-called Kashrab invariant, so that is J K of any lambda, and I divide by J U of lambda. So for every weight lambda, not only dominant weight, you can define the Kashrab the invariant. So that is always in the Habiro ring. Okay. Now if lambda is dominant, then this would be just polynomial. Okay. But if lambda is not dominant, this would be in the Habiro ring. So in particular, what I call the Kashrab invariant for generally algebra is the case when this lambda is equal to if lambda is equal to minus rho, which is the sum, so 1/2 minus 1/2 sum of positive root. Okay. So that is just the center of on this divine group action, and then in this case, the invariant is really in the Habiro ring. In general, it cannot be in the just polynomial. Okay. So as a corollary of the theorem, so for example, if n is an integral homology sphere, then the conjecture of Kontsevich on root Lorentz about the integrality of quantum invariance holds true. So it means that tau and G and C is the WRT invariant psi is an algebraic integer. So it means that it actually belongs to this one thing. Because if you evaluate the universal, the Jm here at the root purity, you see that they are in there. And then there's a recovery of the, well, in the case of knot, you can always recover the Color-Jones polynomial from the Kontsevich integral. And for integral homology sphere, the counterpart of the Kontsevich integral is the NMO invariant. So let me just draw here so we have here integral homology. So that J M will map you to this Habiro ring. And you have the Taylor expansion 1, which maps you to Z of Q minus 1. Now from here, you put Q equal to psi and you map to Z of psi. And that is the WRT invariant. Okay, so this determines this one here. But you can continue this with this. Now you put Q equal to e to the h as usual, and you get into Q of h now. Now you get formal power 3 in h. Okay? And you go from here to here, you lose the integrality because of the nature of this series here. However, there's so this is the so-called the NO invariant will take value in the algebra of dry graph, which unfortunately I don't have time to explain. And this A here, there's for every simple Lie algebra, you have the weight map that map this A to formal power series. And the statements that this diagram here is commute. And from this commutative, you see that the value, if you go from here to here, totally, because this injective is determining this one, and then it's determining this one, and so it's determining this one here. And so it means that the M and O totally determines the WRT invariance. Although you see that it's more complicated than in the NOT case, if you are familiar with the NOT or the link case. Okay. Well, I think that I'm out of time. I'm the last speaker.
You were starting 5 minutes late, so you still have 5 minutes.
Oh, really?
Yeah.
Well, well, I'm the last speaker. I understand that you are tired. I'm also tired. Okay, so this is my gift to you. I stopped 5 minutes early. Okay, so that if you don't like my talk, at least you like the last 5 minutes. Okay. Thank you. Yes?
Is integer very important, or rational also? Rational is yes.
Okay, so yeah, I had this in my notes, but I don't have time. So since you asked, so let me add this here. Suppose the h1 of m z is equal to some number d. Okay. So the best reason that we have now is the following reason, which is often in joint with Lydia Kova and Euler and myself, is that the W, so there exists a unifying invariant, so Jn here. I put here PSL2, so this is actually SO3, which is in the Habiro ring, but I have to use this 1 over d here. So I have to add inverse of this d, so everything will be exactly the same, which recover the WRT invariant. So that if you plug in, so that J and this PSL2 of sine here, this is equal to the, so this is also PSL2 of sine. But the nature of this P here, P is stands for the projective, so it means that the sine must have, just by definition, it must have odd order. Okay, so when, but so far I cannot generalize this statement to other Lie algebra. So this is only for SL2, but in that case, you see that I have to add the inverse of 1 over d of d here, where d is the size of the homology group. Okay, but this ring is not as nice as the original Habiro ring. For example, it is not a domain.
But you expect the same commutative diagram. If anything was existing, you expect the same commutative diagram.
Yeah, the same. No, not quite. It's not that simple. The question about recovery, the WRT invariant from the animal invariant for rational homologous sphere is still open. Okay, the same as the integrality. So we prove here the integrality for every root, but only for integral homology tree sphere. Okay, for SL2C. In joint group with Lydia and my student Chen, we have integrated for every root, but we don't have that result for all Lie algebra and all three uniform.
Yes. Well, just a comment, I would say that I think it's a big challenge to physics to prove via physics techniques what's on the blackboard right behind.
I mean this.
Yes. I don't know of any things from path integrals that can prove this.
Can you prove what?
I don't know.
Prove that the asymptotic expansion of the triple flat connection determines the invariant completely, which is most likely what this LMO is, right?
Yeah, the LMO is supposed to be the contribution of the driven connection.
Or for that matter, you know, do path integrals over the Habiro ring and end up in the Habiro ring.
Other questions? Okay, not, let's. Thanks.
Thank you.